This video was produced by the Aluminum Association for use as an introduction to the prevention of and protection from molten metal incidents in the aluminum cast house. Extensive additional information on these topics are available from the association, both in the form of written guidance and in person during Casthouse Safety Workshop training sponsored and organized by the Aluminum Association. This video is intended to supplement but by no means replace these more in-depth and detailed resources that are available. For further information, please contact the Aluminum Association using the contact information shown. My name is Mark Iliopoulos with Kaiser Aluminum. I want to cover a couple facts around molten aluminum explosions. Nothing we do within our industry can have a greater impact and consequence on people, property, equipment in the business than a catastrophic molten metal explosion. Do you believe that fact? Nothing we do can have an impact on people, property, equipment in the business like a catastrophic molten metal explosion. Yeah, I think that's very true, and I'll explain that. Quickly, you can see that. 50 years ago, this event happened. You see that the massive destruction on the casting complex. 4 people were killed instantly, 1 later. Catastrophic event. So you ask yourself, can that happen today? Just 10 years ago, 16 cast houses workers were killed and another 58 seriously injured. 10 years ago. More recently, August 4th, 2015, massive explosion at a cast house. You can see the massive structural damage. Fortunately, no one was injured significantly and no deaths in this event, but you could see the potential. And then just over a year ago, another significant explosion, serious injuries, but obviously serious impact to property, equipment, and the business. Fact number 2, preventing molten metal explosions is the Aluminum Association's #1 safety priority. Tremendous focus, effort, and energy is applied by the association in pursuit of explosion prevention. So within the association, that's the #1 safety priority, and it's an absolute must. Fact number 3, we melt, transfer, and cast hundreds of millions of pounds of aluminum year after year safely and without explosions. And I'll give you an example. This example shown is one member's company data, but really is representative of almost the entire industry. And we'll share with you the raw data for explosions shortly, but this slide represents one company's data over a 10-year period, looking at millions of pounds produced. In other words, exposures considered here. As you can see in apply exposure, pounds cast, explosions are indeed rare events. The average explosion rate of this company is 0.003 per million pounds cast. So even though we have these significant events with severe consequences, the industry as a whole, when you think about pounds cast per million pounds cast, is significantly low. Another situation we have, of course, is with injuries. In this case, it's OSHA recordable rate. And if you look at the blue line, that's all manufacturing within the United States. The red line is the Aluminum Association member companies. So in this 12-year period, so you can see that we've reduced injuries at 37%. Fact number 4, industry experience tells us that molten metal explosions are infrequent events within the industry, but sometimes with severe consequences. I think you can see by the data I just showed and the 3 explosions in the factories, that statement is absolutely true. Fact number 5, molten metal explosions continue to occur worldwide. So the last fatality that we had from a molten metal explosion was in 2014. Before that, 2009. So we went 5 years without a fatality within the industry as it related to a molten metal explosion. In this particular case, the force of the explosion sent a piece of equipment toward the operator with such force that resulted in a fatality. And the point I want to make here, because we're going to talk about in a little bit, it was the start of a cast. So that's important when we talk about casting and start of the cast. So this event, the last fatality, was the start of the cast. Fact number 6, we know within our industry how explosions occur, their causes, why, and how to prevent them. And as we move forward in this presentation, I'll be discussing these areas in greater detail. Fact number 7, our past explosion incidents and incident data provides lessons learned for today and guidance for the future. As an industry at our Molten Metal Safety Workshop, we examine past data and data that allows us to share experiences, learn from these experiences, and create changes, including new internal standards and industry-wide guidelines that will prevent future explosions. This table is how we classify molten aluminum explosions in terms of force. So there's 5 criteria: property damage, light, sound, vibration, and metal dispersion. So as you move left to right, force 1, force 2, force 3, the more severe explosions that you saw on those photos were force 3 explosions. 2 areas I want to cover because it's easy to really look at these situations and criteria is metal dispersion. So you'll notice when we have a force 1 explosion, we don't see metal going greater than 15 feet. When we say force 2, that's a criteria of 15 to 50. And we see force 3 explosions where metal thrown in great distances, sometimes hundreds and hundreds of yards in some cases. And obviously you can see the degrees where in a force 1 explosion, there's really no property damage, minor property damage. And of course, what I showed you in those pictures were all force 3 situations, right? And so that's how the association, how the association collects data on molten metal incidences by force levels. Anybody astronomers out there? I know we had some scientists and other people, but that's our universe, okay? But I'm going to be talking about the universe of molten metal explosions as reported within the industry. So 200 member companies, 300 plants worldwide provided this data. So busy chart here, but what is shown on the bar chart, all the explosions, all levels, so force 1, force 2, force 3, reported to the association by member companies from 1981 to 2016. A major effort has been undertaken at all Casthouse Safety Workshops, and we had one just this week, to reinforce the reporting of all incidents so we understand that data and have a clear picture of what the data is and kind of what our universe of explosions are. But as you can see, we started off low in the early years, and you can see the mid-years, and if you look at that 150 average between 2000 and 2007, doesn't necessarily indicate we had more explosions. Well, that was a major effort by one aluminum producer to acquire those incidents, get those incidents in, so we shared that data with all the industry. But as you can see, over the last several years, we put a lot of focus on this to make sure those incidents get in so we understand where those incidents are occurring, what processes are occurring in, and share that with members. So when you think about the distribution, you think about all those explosions that I showed you in that bar chart, this is the distribution. So the good news is this: there's obviously more force 1, so minor explosions, some force 2, the 2nd degree, and that force 1 and force 2 are going to be talking about different types of explosions. Those tend to be steam-related explosion or steam-cause-related explosion. But the force 3 explosions, very few in the industry since 1981, but the 3 pictures I showed you was all force 3 situations. That one in particular. The bar chart shown represents all explosions by force level. Somewhat of a busy chart, but you can easily see there is a significantly greater number of force 1 explosions represented by the blue bars versus force 2 in yellow and force 3 shown in red. This next bar chart removes the force 1 explosions and only shows the higher level explosions, force 2 in yellow and force 3 in red. Here you can see that the force 2 explosions have averaged slightly over 22 explosion events versus force 3 at just slightly over 2 per year for the historical data reported to the Aluminum Association. Both of the historical averages are represented by the horizontal lines you see on the chart. This next slide only shows forestry explosions or the highest level explosions reported to the Aluminum Association. As the chart shows, we have seen a decline of forestry explosions over the last 10 years and even a greater reduction over the last 5. Hopefully, we can contribute that reduction to the efforts by our industry and the Aluminum Association, which continues to promote and focus on the prevention of all explosions. Now, of course, as you might expect, with explosions comes injuries. So this is what injuries looks like in terms of data from 1981 to 2016, 1549. And again, they're ranked in terms of minor being first aid, serious medical treatment case like we think of OSHA recordables, and of course fatalities. And that data looks like that. Again, about the same distribution as the force level explosions, but unfortunately 91 of those have resulted in fatalities. So somewhat of a concept. We don't have the ability to lock and tag out potential stored energy in molten aluminum. So if you think about what we do at our sites and we have potential energy, we have the ability to lock out potential energy. With molten aluminum, we don't have to, we can't do that. So what we have to do, we have to manage that risk differently. And I'll be talking about how we manage some of those risks. So we think about explosion, here's a definition. How do you know explosion occurred? Molten aluminum or solid charged materials are launched into the air and leave their container space within, the container and result in a steam or chemical reaction. So if you think of some of those containers, anybody have any ideas about containers in our cast houses? Furnace, yeah. Drain pans, okay. What's that? Yeah, there you go. All those are good. All those are correct answers. So when you think of cause of the explosion, we'll talk about steam explosions. Water trapped in or under molten aluminum. So think about that. Water trapped in or under molten aluminum. Also chemical reactions. So the first two are really going to be the force 1 and force 2, the vast majority of those. The force 3 are really going to be that second one, or those chemical reactions. And of course we know some of those are caused by ammonium nitrate, fertilizer. We know the power of ammonium nitrate. So ammonium nitrate in molten metal, right, is a catastrophic event. So what causes most molten aluminum water explosions? Steam explosions, water trapped in or under molten aluminum, or exothermic chemical reactions? That's the answer. So most molten aluminum explosions are caused by water trapped in or under molten aluminum. So this gives you kind of a pictorial view of how that process occurs. Water trapped in or under aluminum superheats. That water rapidly changes from liquid to a gas, in this case steam, and expands up to 1,700 times. Steam explosion occurs, spraying molten aluminum in every direction. It's a steam-caused explosion. What does 1,700 look like in terms of volume? So if you took a marble, 1,700 times, you get a soccer ball. For some, I know someone, that's a football, right? Okay. Anyway, tremendous expansion. What if we have moisture in the sow cavity, okay? What does that look like? So think about that in the sow cavity, that marble expanding 1,700 times. The pressure's got to go somewhere, right? So you get the concept? Okay. So now we're going to talk about cavities that we have to deal with and manage the risk. So these are some alloying agents that obviously have cavities and have the potential to contain water, and then, of course, convert it to steam if it gets into molten metal. And that was aluminum. Of course, we have cavities in alloy material. Same situation can occur. So again, here's an example. How can water be trapped in or under molten aluminum? So we think about sow with moistures on the surface, or water in a sow in a shrinkage cavity. Which one's going to be more potentially dangerous? Because obviously we know this by experience. These sows contain up to a gallon of water in one given sow. So think about that 1 gallon of water 1,700 times. All right, this is an important point here because up to this point, we really talked about explosions caused by steam, water trapped. To this point, and what I want to say here is that the steam-related explosions really account for, and I think I mentioned this, the primarily force 1 and force 2 explosions. However, as we know, aluminum is a very reactive chemical element with a great affinity for oxygen. Just as is required a large amount of energy to break down the aluminum-oxygen bonds and produce metallic aluminum, that energy will be released if aluminum is able to be recombined with oxygen or oxygen in either water or air. So that's this exothermic reaction that you see up there resulting in this. So if you think about it, this has been estimated from a thermodynamic standpoint, that the release of energy of 1 pound of aluminum fully reacting with oxygen is equivalent to detonating 3 pounds of TNT. So you get a perspective of how violent that can be if aluminum is able to react with oxygen in either water or air.
This next animation illustrates what would be the likely outcome if a 1,500-pound sow with an internal shrinkage cavity containing water was placed into a furnace with molten aluminum. First, the sow would become submerged beneath the molten aluminum inside the furnace. The molten aluminum would freeze on the sow's surfaces, essentially sealing the sow and trapping the water inside. The trapped water eventually turns to steam and pressure develops within the sow cavity. Somewhere around the 10-minute mark, an explosion occurs, likely in this case a violent explosion. We know this based upon past explosion events involving submerged sow with cavities that 10 minutes lapse time is generally what it takes for an explosion to occur in these circumstances.
All right, so that was one example of a situation where we can trap water. Here's another one. We face this all the time in terms of charging metal, closed containers, and I think you can see the problem with the picture on the left and the picture on the right in terms of crimped tubing. All those can contain water. All those are dangerous. All those situations can trap molten aluminum, trap water in molten aluminum. Other contaminants face as an industry in charged materials. So foreign materials in the furnace cause a lot of problems besides safety, but also a potential for an explosion. Another situation, we talk about steam explosions, water on starting blocks, bleed outs at the start of the cast, wet, drain, and skim pounds. So just to cover some explosion research. So we know what happens on these events, but the industry started in 1949 to 2001, did a tremendous amount of research on molten metal explosions and really helped develop an understanding regarding what promotes and prevents explosions. So we know what causes them and we know how to prevent them based upon that research. And so some of, or all of actually the protective coatings used in our casting pits today came out of that explosion research.
The following short video clip shows you the test method used to evaluate coating effectiveness in the prevention of molten aluminum explosions. The testing was conducted at the Alcoa Tech Center under strict control conditions, applying multiple safeguards to protect all participants involved in the testing. In this explosion test example, 50 pounds of molten aluminum is dropped into a 1-foot square steel container with approximately 6 inches of water inside. In this clip, the container is not coated with protective paint. Other videos in the series of testing show the results of both coated and non-coated containers. I encourage you, if you've not already done so, to watch all the testing so you understand the importance of protective coatings. 50 pounds of molten aluminum is safely transported in a temporary crucible and poured directly into a crucible at the testing apparatus. Once the technicians are safely out of the area, the cover protecting the steel container is pulled away and the metal above is dropped directly into the container containing the water. As the video shows, there is an immediate and violent explosion as the molten aluminum traps the water on the uncoated surfaces of the container. As you can see, the crucible on the test apparatus was blown away and molten metal was thrown from the testing area to the surrounding fence line over 50 feet away, catching the grass on fire. Explosion test videos are available from the Aluminum Association and are highly recommended for individuals that work within your cast houses.
That was easy. All right, these are the conditions that help prevent explosions. So high water depth in pits. So we always want water depths greater than 30 inches. Dried or oiled surfaces, protective coating. So we always want protective coatings approved by the Aluminum Station on our pits because we know in order to prevent explosions, we have to have those coatings in place. I want to cover 3 critical processes: melting, metal transfer, and casting. Which of the 3 cast house processes we know have the most force 2 and force 3 violent explosions? What would you suspect? All right, good. Melting was number 1. And that's what the data says. So when we look at all those explosions reported, 3,535 within the association, we see that force 2 and force 3 explosions within melting were the most severe. We certainly have force 2 and force 3 in other processes, but they're more prevalent in the melting operation. And you can see how that can occur in our melting furnaces. Which of these 3 cast house processes we have the most injuries as a result of explosion? Melting, transfer, or casting? It's in casting. Why would it be in casting? Yeah, more people around, exactly. More exposure, okay? We tend not to have a whole lot of people in charging. We should never have a lot of people involved in the charging area, right? Good. And one of the things, of course, we have more injuries in casting, but you know, if you're in a molten metal workshop, I mean, a lot of advances are occurring in hands-free casting, so we're getting rid of that exposure, and over time, that number will be definitely down. Which type of charged material accounts for the most number of melting explosions reported to the association? So the charged material that we put in our furnaces, what would you suspect? Scrap, okay, all right, good, excellent. If you look force 1, force 2, the first thing, scrap, yeah, way out in front of everything else. And you can see wet surface scrap, trap moisture within scrap, yeah, huge potential. All right, well, here's a video, it really scares me. So here's an idea. We charge in a furnace, here's a charge car. Watch what happens. So materials going into our furnace, very dangerous potentially. Pretty significant, huh? Yeah. Think that might be combustible dust? Could be, right? Another hazard. Different subject, but another hazard. So just some key, we think about protective measures, protective systems, safeguards. So in terms of melting, some key points I want to make. Metal purchasing, inspection, and storage are critical. I mean, those are really the first line of defense, is speccing out the material you expect to get in, making sure you get in and inspecting it thoroughly, because that's really the first line of defense before it comes into your cast house. And then, of course, where you store it's very important. And all materials that you have in your cast house need to be stored away from outside walls where you can get contaminated and wet. And if you dry materials, of course we do dry materials, we have to dry sal, we have to dry alloys. Those need to be marked. You need to have a time-stamped date on those, so if they're sitting, they don't go into the furnace, because if they can collect moisture, and then the hazard will reoccur. Then the last one I want to make a point about is charging must be done right every time. And the point I make at the end, only as strong and as good as the new hire on 2 a.m. So it's really critical that training be a part of this, and your processes be sound, and your checkpoints and verification be sound, because it's only as good as that guy on 2 a.m. to try deciding to charge or not charge that cell. Talk about metal transfer, and you can see obviously from a force standpoint, that may be surprising, but again, we still have catastrophic type explosions during transfer. So it's just not in melting, just not in casting, but also in transfer. And again, you might see injuries and fatalities, that may be a surprise, but people get injured in the transfer process. Why? Because they're typically around the transfer units in the trophy. So some really critical things here, and I'll show you some photographs and I'll show you some examples here, but we see wet contaminated tools, drain pans, wet troughing. And really critical here is oftentimes these situations are because of delays in the production process or repair. So that should be a red flag for everybody. So when we talk about transfer, we should be thinking about when delays occur and when repairs occur, because that's when these events can and have occurred in the past. All right, here's what happens with wet tools. Watch the guy on the troughing, blew right back on him, burned. This was a fatality event, okay, from sticking a tool into molten metal. This is a drain pan explosion. I talked about drain pans. Watch this event. Force 2 explosion from water in a drain pan. Molten metal trapping water. So as you might expect, seeing those two videos, key to success is we've got to make sure our tools and equipment are dry. In terms of drain pans, we've got to make sure they're dry or oiled. We want to preheat furnace tools and hand tools before we insert them into molten metal. And we've got to make sure all the refractories are dry. Lastly, casting. There's the force distribution in casting. So we see primarily force 1, some force 2, significant amount of force 2s, of course some force 3s. Look at casting injuries, significant because why? Because people are around. During what part of casting process the explosion occurred? I kind of queued you up for this one. Yeah, startup. I mean, the last fatality within the industry, right, was a startup. There's the distribution. So when you're thinking about being in a cast house, if you're a casting operator, you got to do all the right things up front. But again, if you're visiting the cast house, you want to be in there in the startup process. Okay, the most dangerous startup, most dangerous time to start up. All right, start of a cast. Watch him pull the dams, watch what happens. One of the good things here, and as we share within the cast house, look at the PPE they're wearing. Okay, so they're maxed in terms of PPE, so they know the exposure is high. They know this is a potential. They know startup is an issue. You see that explosion? Yeah. This is a hang up resulting in a bleed out. This is kind of a graphical depiction of what happens. I think it hangs up in the mold. Do we have that periodically? Yeah, not often, but periodically. Cooling water's on the starting block. See metal coming down into that starting block after it descends. That water's trapped in or under molten aluminum. What's going to happen? And there's explosion occurs, okay? Could be force 1, could be force 2, and in these situations we've had force 3s in the industry. And here's the force 3. Here's an example of a force 3. No fatalities, but look at the position where they're at in terms of the casting table. Okay, 3 serious, critically serious injuries. So 2 key ways to minimize potential when casting explosion bleed out occurred. Of course, we want to make sure the protective paints are there, and at least 3 feet of water in the casting pit. Very, very important in protective systems to prevent massive explosions. So how do we manage the risk in the casting process? Of course, we have to eliminate all sources of moisture, starting with tools and refractory. So the tools that we use in casting, refractory materials, we got to make sure are clean and dry. We need to eliminate all the opportunities for bleed outs and hang-ups. So the 2 of the most critical hazards we have in casting is bleed out and hang-ups. And we do that really with equipment condition. You have to start with equipment condition, and then your practices and procedures in terms of your casting practices. And then you got to make sure your protective systems are in place, namely your protective coatings, things like emergency water. And of course, everyone needs to do pre-start checklist, and almost like a pilot-like, not almost, it needs to be pilot-like discipline, just like that these casting operators need, just like you're flying a plane. That's how critical it is. And of course, if all that fails, and it shouldn't fail, but if it does, you need to have, how do you respond to bleed outs, how do you respond to hang-ups, so you can deal with those immersions safely without putting people at risk. The last line of defense, so I talked about all these protective systems, all these systems within melting, transfer, and casting, but as you can see, sometimes that fails by the 3 pictures. This is the last line of defense. So here's where it all started for me back in 1983. I wasn't there, but there was a lot of industry focus when this event occurred. So what happened, there was a bleed out, molten aluminum occurred, explosion occurred, people in and around that casting table, and molten aluminum went in the air a long ways and set all their clothing afire. So there was 5 fatalities from that event alone. So that should never happen in our industry again because of the protective clothing we wear. So there's what we should be wearing. Everybody in the cast house, primary and secondary clothing, with the primary clothing doing the critical tasks. And some of those examples I showed you, people wearing primary clothing and doing those critical tasks for maximum protection. That's what it looks like, okay? Everybody has a similar variation of that. Most plants use either this or Zerpo wool, but maximum protection during critical tasks. So there's what it costs. So when we outfit a worker in this clothing, $1,070 basically, in and around that amount. But is it worth every penny? Absolutely, it's worth every penny. Every penny we spend on prevention as an industry, and every penny we spend on personal protective equipment. Why all of this effort to prevent explosions? Several reasons. First and foremost, worker safety, business viability. You can see if we don't prevent explosions, catastrophic type explosions, what can occur? Customer confidence. We can affect customers' confidence. We can't deliver their product to their location because our cast house is disabled. Community confidence. We all do business in a community. And it's important that people know that what we're doing in our operations are safe, and industry confidence. So it takes all of us together working to accomplish preventing molten aluminum explosions. So just a couple things from the Aluminum Association standpoint, a lot of resources, a lot of guidance, and just this week, as I mentioned, the Casthouse Safety Workshop, and occurred this week, over 100 people, 108 people, member companies, non-member companies, focusing on the prevention of molten aluminum explosions. And there's some of the guidance documents available. I think some of those are on display. So excellent, you look at the one on the left, guidelines to molten aluminum handling, the newest standards or guidance documents in our industry for the prevention of molten aluminum explosion. Comprehensive document created by member companies. Go back to this fact, preventing molten metal explosions is the Aluminum Association's #1 safety priority. And with that effort, we will continue to make great strides going forward in the prevention of molten metal explosions.
In closing, I would like to recognize 3 individuals that were instrumental in the preparation and review of the materials presented today. Special thanks and appreciation to Ray Richter, John Zay, and Kurt Wells. Overall, I hope you found this session valuable as you go forward within the organization to improve molten metal safety. Thank you.